My name is Matt Turk, and I'm going to be sharing with you a little bit about analyzing and visualizing three-dimensional data in Python. As a bit of background, I was trained as a computational astrophysicist. Nowadays, I spend my time in the Department of Information Sciences, where my colleagues run the gamut, studying topics like metadata, archiving and preservation, artificial intelligence and its applications, comic books, youth library services, game design, and reproducibility. But my background was in studying the formation and evolution of the first stars in the universe. We did these studies almost exclusively using simulations. We start with initial conditions given to us by the matter power spectrum, and then initialize fields such as density, temperature, and velocity in a regular grid that span some chunk of the universe. We integrate the calculations through many time steps, applying solvers to account for gravity, hydrodynamics, radiative transfer, and chemical changes. Built into the simulation code we used was the understanding that not all areas in the universe are equally interesting. Wherever the gas was overdense, or shocking, or genes unstable, the simulation code would insert higher resolution regions through a process called adaptive mesh refinement. This led to things like overlapping regions, regions of higher and lower resolution that are abutting or adjacent, and a sparsity of coverage. Of course, in simulations there are other ways of doing things, and we're also not just going to talk about simulation data today. Often simulations store their data as discrete points with multiple values associated with them. What all of these have in common, though, is that we can apply, or at least safely assume, a metric for distance between points. This gives us a built-in way of applying rotations to a collection of points, and allows for the possibility that coordinate transformations, combined with projections into fields of view, could reveal rather than impose information about the data. What we're going to start out with is a walkthrough of different ways 3D data might be stored, and then we'll talk about how you might analyze and visualize data in different representations. And by the end, we'll be doing 3D volume visualization. So we're going to start out by talking a little bit about what makes 3D data special and a couple of the different representations that we might use to regard 3D data. Over the course of this lecture, we're going to be using many different tools, including NumPy, Matplotlib, Plotly, IPyVolume, Py3JS, and even YT. But for now, we're just going to take a look at a couple different representations of 3D data. So we're going to start out by importing NumPy as NP, as per convention. And we're going to import matplotlib.pyplot as PLT. We're mostly going to be using matplotlib during this first part of the lecture. So the special thing about 3D data is that if we have 2 points, x equals 0.5, y equals 0.9, z equals 0.1, and let's call this x0, and we have a second point, x1 equals 0.1, y1 equals 0.3, z1 equals 0.8. We can get the distance between these 2 points in a pretty straightforward way. In fact, we know that the distance is going to be x1 minus x0 squared plus y1 minus y0 squared plus z1 minus z0 squared, and then taking the square root of both of those. And so you can see that the distance here is just a smidge over 1.0. The other neat thing about this is that if we were to rotate these points through some arbitrary angle about one of the axes, the distance is going to remain the same. And that's what makes it interesting to visualize data in 3D in particular, because no matter which angle we look at it from, we're still getting an accurate representation of that data. Now this representation of the data is essentially through discrete points. So there are several different ways that you might see discrete points represented. The first of these is probably something very much like this, where we have several different sets of points. And maybe this shows up as a list of lists. So it might look something like a points, where the first one is 0.5, the second one is 0.9, the third one is 0.1, the second one is 0.1, 0.3, and 0.8. And maybe they even have some attributes associated with them. So let's call these our temperature, let's say. So our third point let's put it at 0.71, 0.9, 0.9, and 200. Now, if we just do this, we get our list back, and you're all comfortable with NumPy by this point. So instead, let's turn it into a NumPy array. And in this case, our array has shape 3, 4. This first column is the identity of the point. So the first point, the second point, and the third point. And this second axis is the dimension of x, y, z, and temperature. So this is one way that you might see your data, and you can imagine that this data might extend out, and this dimension gets a lot longer, and this one stays the same. And we can access this by looking at slicing along the first dimension, getting 0, or we can access it by slicing along the second dimension and getting all of the x coordinates. The second way that you might see this is you might see it with a special D type. And in this case, it'll be something very similar looking to what we had before. We might have a set of points, but instead of having these as a list of lists, they might be a list of tuples. And we might also regard these as having a particular D type. Now I've got too many square brackets here, so let's get rid of a couple of those. But we can specify a particular D type here. And a D type shows up as a list of tuples again. And we get a name and a type for each of the columns, if you will, inside our tuple, inside our D type. And so in this case, I've specified that our D type is that we have a 8-byte floating point value for x, an 8-byte floating point value for y, an 8-byte floating point value for z, and an 8-byte floating point value for t. Now if we look at the shape of this D type, you'll note that it does look a little bit different. So here, each one of these is considered a given value. And if we look at the D type for it, we see what we defined as our D type. And if we look at the shape, instead of coming back as 3, 4, it's actually going to come back just as 3, because we have 3 elements of this type. There's some similarity in the way that this is regarded and the way that, say, complex numbers are regarded, where you have 2 adjacent floating point values, one for the real component and one for the imaginary component. You can access this you can access individual fields if you like in this, but you can't, because it has one sum, you can't sum up along a given axis, for instance. There's a third way that you might see discrete data stored, and this one is a little bit more is sort of a hybrid of the two. You'll see this particularly in I/O libraries, where you have a dictionary of each individual type. Now this is more similar to the way that you might see data stored if, for instance, it is in a columnar store, where each column is stored separately or perhaps adjacently inside a data file. This D-type method is much more similar to what we might consider a row-based style, so where an individual row contains each component. You can think of this as the difference between this 0.5 being adjacent to this 0.5, which is a which is adjacent to this 0.5, which is adjacent to this 100. So this is a row-based store where these are all next to each other in memory, and then the next row comes. Whereas in this case, this 0.5 is next to the x value for the next particle, or the next sampling point is next to the x value of this. And so this 0.5 is quite a ways away from the 0.25 that corresponds to that same particle, the particle's y position. This is the way that you'll probably see it most of the time, and occasionally you'll probably see the x, y, and z as some type of a hybrid, where you maybe have a temperature and maybe a velocity in the x, a velocity in the y, and so on. And you might see the vector components as a hybrid, where you've got a multi-column array inside your overall dictionary-like access inside your columnar store. Other times, however, you'll find the data that you have access to comes in regularly shaped multidimensional arrays. In the past, you might have seen data that comes in a set of columns, like I just showed, where you've got x, y, and z values. But in some cases, it'll come to you in a three-dimensional array, where, say, maybe two of the dimensions are spatial and one is wavelength, or all three are spatial. And sometimes it will have a shape that is 3 plus n dimensions, where n is the number of fields or samples. In a lot of these cases, the data points will be spaced out evenly, but not in all cases. And in some cases, you might find that there's a supplemental array that describes the distance between cell values. What we can try is we can try to create a little bit of fake data for ourselves. Let's create one where we set the center to be at minus 0.05 and where we construct a radius field distant from that. So in this case, we'll set our center to be minus 0.05, minus 0.05, minus 0.05, and we'll do a 1 over r squared field. I'm going to use a construction here, the mgrid construction. And what mgrid does is it allows you to specify a start position, a stop position, and either a step size or a number of steps. In order to get a step size, you would use a real number, and if you want a number of steps, you would use a complex number. And in Python, the complex numbers are denoted with this j. So in this case, I've set an x, a y, and a z running from 0 to 1 with 128 values in each of those dimensions. Now mgrid also works with multidimensional data, so I could ask for all of this to be in one dimension, or I could ask for all this to be in one, and in this case it would be mgrid 0.0, 1.0128j, and then I would slice also in this direction and in this direction. And this would return to me a set of 3 arrays that were filled out at 128 cubed each, but that's a little bit more memory than we need right now. So we're just going to do it this way. Now if we look at these will be columns. So we've got 0 to 1, and note that it's inclusive. And we've got 128 in each. Now we're going to use a trick in NumPy called broadcasting. I say trick, but really it's a pretty rad operation that gets used a lot, in order to make these look as though they were constant along certain dimensions. So we'll say IR2 for inverse r squared is equal to, and I'm going to use a couple parentheses here, x minus center 0 squared. And I'm going to access the x minus center squared array with a slice for all, and then the none object. That'll insert axes there, and it allows us to broadcast. So now the resultant array here will be 128 by 1 by 1, and so if we then do y minus center 1 squared, none, comma slice, comma none. Now this will be 1 by 128 by 1, And now we've put our 128 at the end here. So this is 128 by 1 by 1, 1 by 128 by 1, 1, 1, 128. And this will broadcast itself into an array. This will ultimately result in an array that is 128 by 128 by 128. And we'll take the inverse of it. And so now we've got an array where its values of radius from this point. It's now 128 by 128, and we can slice it. So we could, for instance, take a look at the 0th here. You'll see it's 128 by 128. And this is the singularity where we're doing 1 over r squared, where the r is very, very small here at the very bottom. The other thing that we may find out from this is that sometimes these arrays are shaped differently. If we look at, for instance, ir2.flags, we'll see it is C contiguous, but it is not F contiguous. So C and F here stand for C and Fortran, and they refer to the way that these values are in memory. So for instance, IR2, since it is C contiguous, that means 0, 0, 0 will be right next to 0, 0, 1. So the distance between those 2 points will be exactly 1 value. If they were F contiguous, then the distance between these 2 points would be 1 value. We can also generate an irregularly shaped array, and we can do that by generating some random distributions. So if we were to do random.random 128, you'll see that this gives us a set of values between 0 and 1, 128 of them in fact. What we can do with these is we could actually either sort them. We could actually either sort them, so x.sort, and we can look at them and you'll see that they're monotonically increasing and they go all the way up to just under 1. But there they don't actually get all the way to 1. So we're going to use a little trick where we add them all, but we use an accumulation. And so np.add.accumulate means replace this array with the running sum of those values. So if we had np.array of 1, 2, 3, 4, and we were to do np.add on that array, or np.add.accumulate on that array, we would get 1, 3, 6, and 10. And now if we were to normalize that, it would result in values that run between 0 and 1. So we're going to use that trick here. X equals np.add.accumulate on a random set of values. And now let's do the exact same thing for Y and for Z. And so now if we look at X, you'll see that the first value is here, last value is there, and it'll be the same thing with Y and Z. So for these, we can generate IR2 exactly the same way. Oh, it appears that I have neglected. But now, they won't be regularly spaced anymore. We'll still have a regular grid, but each one of the values will be at different positions. We'll see some things that we can do with this in just a minute, but the important thing to note here is that we can store our data this way, where we have individual fields, in this case the inverse r squared, and we can also store it similarly to how we did in the previous example, where we had dictionaries or where we had collections of data with an axis either here at the beginning or an axis here at the end. Each of those will have different characteristics and we'll use for different things. The last thing we're going to cover in our initial exploration of regular 3D data is going to be how to get a quick overview. Now, for this part, we're going to use Matplotlib for the first time, and we're going to start using Matplotlib in a pretty simple way, but we will move on to more advanced usages as time goes on. One thing that we're going to import here that we haven't imported before is scipy.special, so that we can get a hold of some spherical harmonics functions. And we're also going to import the matplotlib log norm function. This is going to give us a normalization function in log space that we'll use. Now, for reasons that I'll explain in just a little bit, this time we're only going to use 64 by 64 by 64 for our grid size. We'll, just like before, make some data values. And this time we're going to have them run from -1 to 1. And we're going to have them be 64 by 64 by 64. And so for our x, our y, and our z, we'll initialize like that. Now the next thing we need to do is we're going to apply a coordinate transformation so that we can be in spherical coordinates. And for this, we'll do the standard of np dot square root of x times x plus y times y plus z times z. And then for theta, we'll use the arctan2 function. And I want to make a quick note that in this particular way of defining things, we're going to have theta running from 0 to pi, and phi running from 0 to 2 pi. That's the opposite of what scipy expects in the function we're going to call, but it aligns with what I usually personally utilize and what I think is more common in some areas. So arctan2, so that we have the quadrant information, is going to be the square root of x times x plus y times y, and then the second argument will be z, and we'll define our phi as arctan2 of y and x. Now let's take a quick look at what we're going to do next is we're going to generate spherical harmonic values for these. And to do that, we're going to utilize the convention that our data will be stored inside a dictionary where the keys are the field name. And so we'll initialize our dictionary, and we'll use n of 1 and 4, and we'll do m, just the positives, in range n plus 1. And we'll define our data value, and I'll use an f string here because I've started using them recently and I just can't get enough of them. We'll define this as np, and we'll use the absolute because it gives us back complex numbers. Spherical harmonic with m, n, phi, and theta. And again, it says in its description that it's theta phi, but we have opposite values for that. So now we have our data array filled with all these different things. And there are a lot of different ways that we can do an overview of this data. And the very first one we're going to try is just to do an IM show on it. Now, I know this seems a little bit anticlimactic because we're doing three-dimensional data visualization, but one of the best ways to get an overview of things is to do dimensionality reduction as a first step, and so we're going to do that. And so I'm going to do IMShow, and I want to point out that I'm selecting all in the X, all in the Y, and I am doing the integer division of n divided by 4. So that gives me about a quarter of the way in. I'm going to specify the extent, and then we'll do a color bar. All right, well, that looks like a spherical harmonic to me. Let's try a different one. This time, instead of doing a slice, let's go n1, m0, and let's do a maximum. And this time we'll do it along the 0th axis. And we'll again specify our log norm. All right, still looks like a spherical harmonic to me. The next thing we're going to try out is we're going to start to use the IPyWidgets library. IPyWidgets is a pretty fast way of adding interaction to items in the Jupyter Notebook, and we're going to use it here to help us get a little bit more seamless of an overview. So we'll import IPyWidgets. And there are a lot of different things that you can do with IPyWidgets, but we're going to use the interact decorator. If you haven't seen the decorator syntax before, you use an @ symbol, and then you have a function, well, sometimes a function, but you have an @ symbol, and then you have a function defined beneath it, and it modifies the execution of that function. It essentially, it wraps it. So we're going to specify that we have a couple different options we want to be accessible to our interactive function. The first item is data set, and if we say list sorted data.keys, interact will see that and see that it is a list of string values and give you the option to choose which of those string values you want. The second thing that we'll provide is we'll say slice position, and here note that instead of a list, it's a tuple. And I'm saying that it can run from 0 to n-1 with a step size of 1. Now, if I were to specify these in floats with a step size, it would allow me to specify floats in the widget that comes back. But these are just hints for how interact will see different options. If I were to add something like log equals false, it will know that that needs to be a Boolean operation. And there are some other ones that you can do as well. So now here's our function that we do beneath that. And we say dataset slice position. And note that here dataset is linked to the argument that we specified here. Slice position is the same name that we specified here. And every time we interact, it will call this function with a new set of values. So everything we put inside this function is our interactive widget. So let's take data and data set, and then we'll say slice position. And actually, let's put extent on here as well. And so it pops this up, and we now have our spherical harmonic. We can choose each one. We can change our slice position. And you'll see each time I change it, it clears the resultant output and calls this function and puts the output of that function into here. There are still some artifacts we want to get rid of, and one thing that we probably want to do is we want to have a fixed color bar. So let's see if we can clear this up just a little bit, but not too much. So here, let's specify our Vmin and our Vmax to log norm. We'll say 10 to the minus 3 and 1.0, but we can actually, one thing that's very common to do is to look at the data set and take the global minimum and global maximum. So let's say MA is equal to data set max, data set min, and so Vmin equals Mi, Vmax equals Ma. And so now, as we slice through it, you can see that the color bar never changes, and so we can do direct comparisons between one slice position and another. This is one way to get an overview, but it's also extremely reduced. We're only seeing a slice along one axis. So instead, let's take a look at what we can do for adding additional axes to this. So we'll set up another IPyWidgets interact, and this time we'll provide the exact same argument here, sorted data keys for the data set, but let's provide a slightly more extensive set of options for our positioning. Now here we've used slice position 0 to n, and that doesn't actually reflect the physical coordinates. It only reflects the slice coordinates. So let's modify that. Here we'll go from -1 to 1. And in order to translate that into slice positions, we'll have a step size of 2.0 over n. And we'll do the same thing for y. And for z. Now we'll make our plots again, accepting data set, x position, y position, z position. And now what we need to do is translate our floating point coordinates back into our slice coordinates, which fortunately is not so bad. Xi, we map from -1 to 1 by offsetting by the left edge and then multiplying by our new domain. So this is the integer of x times n plus 1.0. The integer of x plus 1.0 times n. Now I promised myself I would only do this in one take. So now that I've had a crisis of confidence, x plus 1 divided by 2 times n. Yes. And yi is equal to integer of x, or of y plus 1 divided by 2 times n. Zi is integer of z plus 1 divided by 2 times n. And now let's go ahead and get our data x. And this is really just to have everything here in single variables. Data y is data set, but now we slice along the y direction, and data z. Now we want to link our vmin and vmaxes here. For this particular case, we will go ahead and we will set our minimum equal, just like before, to data set minimum. Data set minimum, and our maximum again to data set dot max, so that we have unchanging color bars for any given data set. We're going to use the PLT subplots command in matplotlib. We're going to say figure and axes are PLT subplots, and we want 2 rows, 2 calls, and because we want this to be a crisp and large sized figure, we'll set our dots per inch to 200. Now what PLT subplots returns to us is, this set of axes, and it's 2-dimensional because I haven't asked it to flatten. So our x will go here. So IAMShow of data x, norm equals log norm, vmin equals mi, vmax equals ma, and we'll set our extent And we'll do the same thing for IMX, or for IMY and IMZ, except here, let's have our Y be here, and we'll set our values to Y and Z, and we'll delete our axes here. Now, we really want a color bar on this, so we'll supply it IMX. Note that we've linked our log norms here, so we can specify any of the image axes as its input mappable. We'll have it output here in the axes object. And you know what? Let's not extend it. We want it to be about a fraction of 0.1. I missed a parenthesis I added an extra close parenthesis here, and so I've removed that. And so now, as we modify each one of these, we're slicing in physical coordinates with an unchanging color bar through our spherical harmonics. Now the last thing that we're going to do is we're going to attempt to utilize Plotly for an isosurface object. Now I had a bit of trouble with getting the Plotly library to work with my Jupyter, but I think that's probably specific to my installation. We're going to go ahead and we're going to import Plotly graph objects as GO, and we're going to create an isosurface plot. An isosurface plot gets used when you're attempting to draw out areas of constant value. So it constructs surfaces where values remain constant. For three-dimensional data sets, this is very useful in order to identify structure and so on in them, where you have fields that are varying slowly or monotonically. So we say isodata is graphObjects.isosurface. And one of the things about the isosurface operator in Plotly is that it requires that you have your x, y, and z values flattened. So we can utilize our x flattened. We'll use np.mgrid here, and we'll say x flattened, y flattened, x full, y full, z full. Go from -1 to 1 with n times 1j. And remember, in the previous notebook, I talked about how you can do this in order to have three-dimensional arrays. And so this will provide to us our x array, our y array, and our z array. And so we specify x is equal to x flatten, xf flatten, y is yf dot flatten, and z is zf dot flatten. And then our data values that we want to look at, why don't we use the ones that we used up here? So that was SPH N1 M0. And we flatten that as well. And we specify our minimum isosurface value and our maximum isosurface value. In this particular case, why don't we go ahead and set our minimum isosurface value to 0. And let's set our iso max surface value to 0.4. We can ask for a specific number of surfaces. As well as the number of ticks, and that's all we really need to do. And so now we have our ISO data, and we'll generate a figure from this, and then we display our figure. Now, one thing that I've run into with this is, and you'll note here that we're only using 64 values. One thing that I've run into is that as you go to higher and higher values, things behave a little bit more strangely. For instance, if you're doing a very, very large set of values, the message from the server to the client, gets truncated and so on. And so, for really big data, this doesn't always work the best. I think in this particular case, it's also exacerbated by the fact that I chose 0 as our minimum. We'll try it again with an ISO min of 0.1. In the next lecture, what I'll do is I will show you how to use other libraries like IPyVolume in order to avoid some of the issues with isosurfaces being generated with Plotly. Now, of course, we can also modify this, where, for instance, we can change which data set we're using. So if we go to N4M3, we might have a little bit more luck. And we get an interactive figure that we can view. So this concludes the first part of the lectures. I will be presenting information about how to utilize IPyVolume and Three.js, as well as how to do overviews of discretely sampled data in the next lecture. Thanks very much, everybody.